We're going to continue our exploration of growth models in this problem down here, in which we're given some data and asked to write the model first and then to use that model to make some predictions or to extrapolate a little bit. So we say in a research experiment, we observed that a population of fruit flies is increasing according to the law of exponential growth. We can maybe make a graph of their data over time and observe this. So we want to come up with a model, but all we know is this: after 2 days, maybe a really poor science experiment, you should probably know this, but if we only knew that after 2 days there were 125 flies and after 4 days there were 350 flies, we want to be able to answer questions like how many flies are going to be after 6 days. So use a model for exponential growth listed above, and I notice above, again, we're sticking around with these two growth models right here. And so we're dealing with growth. We have this y equals a, where a is our initial value, that's a, times the natural base e to the bx, where b is going to be our rate. It is our rate. Okay, so we do not know the growth rate on this one, but we do know some data points. The interesting thing is this: if we were to write out this growth model, let me go ahead and do this. We say y equals initial amount e to the rate times x. What I want you to understand is whenever they give us a time value, what they're doing is they're giving us this x right here. So we could rewrite this model really as this. We could say the amount of flies at any given time is equal to lower a, we'll call that an initial amount, e to the rate times time. These are the same models, okay? So we're given 2 days, produced a population of flies of roughly 125, we say we observed. And also, we say after 4 days, we observed that, you know, it was at a height of 350. And so if it's following this model, what we could do is we can actually just plug in what we know. We say some time and some amount at that time for each of these, time and amount at that time. And we can come up with two equations and actually solve a system to get what we need for our rate and our initial amount, okay? And then we can write a model. So I'm actually going to carry this around the screen here, so you have to apologize. I'll have to apologize here, but we say, all right, let's plug in what we know for this first data point for sure. And we knew that the amount was 125, so I'm going to plug in 125 for the amount, and I'm going to say this equals the initial amount, which I don't know, times e to the rate times time, which I also don't know the rate, but I do know the time was 2. And I also know my second equation here produced a population of 350. This was some initial amount times the base e to the rate times the time, and the time was 4 days in that instance here. So what we're going to have to do is we're actually going to have to solve this system of equations. We have two equations, but I also want to point this out. We have two unknowns. And so last time I checked, when you have two equations and two unknowns, we're either going to do a graphing method, we're going to do a substitution method, we're going to do elimination. In this instance, since these are not standard form, say linear equations, we're going to have to do a substitution method. So what you're going to see me do is this: I'm going to pick a variable here, either a or r, in one of these equations to isolate. And you'll notice that it's really easy to isolate the a's. I'm going to suggest using the one with the smaller values in it. But if we really isolated this a here, it means we would divide both sides by e to the 2r. Okay, so let me rewrite these up here. We say 125 equals a e to the 2 times t is what I'm going to write here. I'm going to divide both sides here. Or, oh, pardon me, 2r, 2 times the rate. Get my colors right here. 2 times the rate. We're going to divide both sides of this by e to the 2r. And so what this is going to do is, it's at the very least, it's going to get a by itself. So we know what a equals now. A equals this entire expression. So what we're going to do is this: we're going to use a substitution method. We're going to substitute this value right here, in for a into the other equation, which was, by the way, 350. So we have a, e, to the, this one was to the 4r. I'm going to readjust those around here. But when we plug in this expression here, I get 125. And in the basement here, I get e to the 2r. So now we're going to have to just do some algebra. Essentially, we say 350, algebraically speaking, 350 is 125. Now, if I put this over 1, you can see I get 125 e to the 4r over e to the 2r. And since we're dealing with exponential stuff in the first place, let's remember our rules of exponents that say when you divide two things that have the same basis, we could write this rule out. We say x to the a over x to the b is equal to x to the a minus b. So we can take the difference of their two exponents here, and we get this. We basically get 125 e to the 4r minus 2r, which is 2r. So now this is just some exponential equation. We've solved about 5 million of these. We're going to divide both sides by 125. I'm going to suggest entirely that you leave this as a rational quantity. And I know that 5 goes into both of these. Actually, 5 goes into this one up here. I think like what? Let's see, 570s. 570, 7 times 5 is 35, and add a 0. And then we say 5 goes into this, you know, this would be 5 quarters. So could we reduce this even further? I suppose we could. We could say 5 goes into this one up here 14 times. Yes, that's awesome. And then we say 5 here. So we've got this. We've got 14 fifths as a reduced quantity here is equal to e to the 2r. Now we are going to undo this. We've isolated the base. We're going to undo it and rewrite this as a log. So we say, and I don't often do this here, but I'm going to write log. Our base is e, and e turned into this quantity here, 14/5. And the way it did so was by taking it to this power 2r. So we say 2r. So the only thing we have left to do here, the only remaining thing we have to do is solve for this rate, which is one of the things we needed to know. So, oops, sorry, divide by r. Come on now. Divide by 2, both sides. But we have the rate. And the rate now is equal to log base e, so ln, of 14/5 over 2. So we can just get a calculator out now and evaluate this. We say 14/5 first of all. 14 divided by 5 is 2.8. And we say take the ln of this. So ln of that, and we're going to divide this in half. So we say divided by 2. And we see we get a rate. I'm going to take this rate out to, like, I don't know, I want to be accurate here. How about 4 decimal places? 5148. So our rate, I'm going to write this down, is approximately 0.5148. And I want to point this out. This is like a 51.48% rate. Okay, so there's a rate. Now we just need to find the time. Now when you solve a system using substitution, the deal was this. If you knew one variable, you plug it back into the other equation to find the other variable, which in this case we need to know the initial value, initial amount. So I'm going to borrow from our first equation, since plugging it back into either equation in the system is going to make you have a satisfied statement here. So we say 2 times r, where our r is 0.5148. So again, it's just algebra. We're going to get a by itself here. But perhaps, we could recognize that we'd have to divide both sides by e to the, 2 times, 0.5148, pardon me. So here's what we're going to do. I'm actually going to get e to the 2 times this first. So I'm going to take this times 2. That's in my exponent. And I'm going to add this to my memory here on my calculator. I'm going to say I want to take e to the power of, so we say e to the power of my memory recall, that thing, is this. And I'm going to divide 125 by this. Now I've got kind of a weird way to do this. Actually, I'll just add to the memory here. We say memory clear, memory plus. We'll take 125 and divide it by our memory recall, which it says is about 2.8. We get A is 44.64. We get A is approximately 44.64. Now this is way awesome because we solved this system for the rate and the initial amount, which means we can write a model now. We could say this is y equals our initial amount, e to the rate times the time. So here's our x, we could say x. But our rate was 0.5148. Just throw that in there. And we say we must have started with an initial value of flies. This is kind of fun. 44.64 flies. So if we were to, say take a look at this graph here, we could go type this in. Let me get these graphs out of here. We had f of x equal to 44.64 flies times e to the power of, and our rate was, I remember it was 0.5148, and we'll call this x. So we say here's our growth model over time, and actually, we could zoom back in here. We could see that, as the number of, I guess, was this hours or days going by, you could see the population of flies growing here. Let's readjust the window a little bit here. We say starting at time -1 and going out to 10 years later, or 10 days later, we'll start a population of 0, and we'll go up to like 500 flies. But you can see how this, it started off here with an initial value of 44.64 is what we said, and with the growth rate it had, we said at 2 days, we can see here it had 125. At 4 days, let me zoom out here. 4 days, we can see that it had, I'm just approximating here. It's just a model, 350 exactly. So we got our data points right. But that's how you would write a model. You'd have to know the initial value and the rate. But once you have those things, you can write the equation and use that to predict what we want to predict, which was at 6 days, what were we at? So this was one of the data points we wanted. We just use the model now. We say about 587.1. And we say at 8 days, which, look at this, check this out, 8 days, I have to go up and up and up and up, 8 days, theoretically, we would have approximately this many flies, 2,750 and a third flies.